Okay, in this video I'm going to show you how to integrate the Dirichlet integral. I've got two ways to do it. I'm going to do the Laplace transform and then secondly Feynman's trick. Okay, so what we're going to do first is replace x, because it's a dummy variable, with t in order to get the method for Laplace. So we're going to do from 0 to infinity, and then we're going to do Laplace of sine of t all over t, and then this is obviously evaluated at s for dt. So this can be just rewritten as the integral from 0 to infinity of sine of t over t e to the minus t dt. Now this can be rewritten as the limit as s tends to 0 of s to infinity of Laplace of sine of t evaluated at theta d theta, and that is a common integral that you can just take for that. So that is the same thing as essentially saying that. So all we need to do now is rewrite sine t in terms of the Laplace transform, and then that as we take the limit of s tends to 0 from s to infinity, and that is just a common identity, so you can say it 1 over sigma squared plus 1 in terms of, well, it'll be 1 squared, but it's obviously just 1 in terms of d theta. Now this is a common integral identity, and we can just say that that is simply arctan evaluated at theta. However, this is between the limit of theta, infinity and s. So if we take the limit, we're not going to plug in infinity, if we take the limit from, let's say, b to infinity, we get that arctan of b is pi over 2, and if we take the limit as s tends to 0 of arctan, we get that equals 0. And so we say that for the first Laplace transform version of this, from 0 to infinity, sine of x all over x dx can equal pi over 2. And so that is the version for the Laplace transform done. Okay, so the next method we've got is the Feynman's trick, or it's differentiating under the integral sign. So firstly, what we're going to do is set this to be equal to the integration of I of the parameter b. So that shows we're going to have to involve no parameter. Now, in this question, this is the main problem, the divided by x. So we need a way of getting rid of this, and that's what we're going to do in this technique. So firstly, we need to times it by another function, and we need obviously times it by a function that is going to be 1 essentially. So we can do that by doing the integral from 0 to infinity of sine x over x. Now we're going to times by minus b, so that's going to be our new parameter x in dx. So the only way this is true is if b equals 0. Now that, because this is going to be 1 then, because if you take b to be e to the minus 0 equals 1. So another thing to note is that b has to be greater or equal to 0. This is because if b is minus here, then this becomes a plus, and therefore e to the bx will just diverge, so we can't have that. Now what we're going to do here is differentiate this, and this is where the Feynman's trick comes in. So we're going to differentiate this, so we're going to do d to the, in respect to b, d to the b from 0 to infinity of sine x over x times e to the minus x dx. So what I'm going to do is put the derivative to the right of the integral. Now when it goes to the right of the integral, it's no longer a single derivative, it's partial, because you've got factors of x and b. So what we're going to do is do the integral from 0 to infinity of the partial derivative of b, like before, and then this is going to be sine x over x times e to the minus x, and then this is obviously with respect to dx, that doesn't go anywhere, that stays there. So now what we can do is rewrite this as simply e to the bx of cosine x plus b sine x, and that will be over b squared plus 1. And this is getting evaluated from 0 to infinity, so we'll put our bounds in, and then so we can compute that when x because it's with respect to x. Now this is straight away we can say that when x infinity is 0, so the first one just becomes 0. We have minus the fact that cosine of 0 is going to be 1, but this will be 1 over 1 when sine is 0, that's going to be 0, and it's going to be all over b squared plus 1. So you get that it is minus 1 over b squared plus 1. Okay, so we've got this part here, which is that. So we can say that the I prime of b equals minus 1 of b squared plus 1. Now what we can do is just integrate both sides. So if we integrate this with respect to db and this with respect to db, we get that this is just ib, and then this is minus arctan of b plus c. Now what you'll notice here is ib is exactly the same as the original function. So we've got the original function. So what we can do, this one here. So what we can do is set this equal to this. So I'm going to rub a bit of this out. Put this here out. I'm going to say that the minus arc tan of b plus c equals the integral from 0 to infinity of sine x over x times e to the minus bx dx. Now what would be really helpful here is if we get rid of the side. Now the only way we can get rid of the side is if we let b tend to infinity, because then that will go to 0. So if we do that, we get that minus arc tan of infinity plus c equals 0. This can be evaluated as minus pi over 2 plus c. So we can say that c is equal to pi over 2. So then this is essentially ib, which is equal to c, which is pi over 2. Therefore, we can say that the integral of 0 to infinity of sine x over x dx is nothing more than pi over 2. And so that is two ways to integrate the Dirichlet integral. The second one's a bit more complex, but it's more mathematical, and the first one is quite simple.